Today we're going to be looking at some integrals where they're a bit more complicated to integrate. You can't just find an antiderivative, and you can't use substitution in any way. So there's three skills that I'm going to show you today. One is completing the square to be able to break something up or rewrite it or be able to integrate using a rule we already know. One is using synthetic or long division to break up a rational. And then the other one is recognizing when, if you integrate, you would get an inverse trig function. So there are two here at the top of your page, inverse sine and inverse tangent, that I would like to bring your memory back to. And just a reminder that chain rule does apply. So if I were to try and do the derivative of inverse sine or inverse tan, and it's not just an x, there's some other function in there, like an x squared or a 3x or something, you must consider that when we do the derivative. And same thing when we integrate. So I have shown you here, for example, if you were to integrate 1 over a squared plus x squared, this would result in the inverse tan of x over a times 1 over a. So this a is all the same a, right? And that's because if I were to take the derivative of the right-hand side, I'm going to get something different. So for example, if I have the derivative of 3x, this is going to give me 1 over 1 plus 3x all squared times 3, because I need chain rule. So the same thing would apply when I do my derivative of this right-hand side. If I do the derivative of this, I need to do chain rule of the inside, which then would help me with my integral. So you are going to want to know these, right? There's one other integral that results in an inverse trig, and that is one that results in inverse secant, and that is on the bottom of your notes. So for example, if I take a look at this first integral here, we have a problem where I can't substitute. If I substitute in u for this whole bottom thing, it's not going to work, and I can't factor this. So I'm going to try completing the square, because I know that that is another technique I have for quadratics. And so if I want to complete the square, just a reminder, that means I'm going to take half of my x term. So I'm going to take half of 6, and that gives me 3. And then I'm going to take 3 squared, and that gives me 9. What I'm going to do is I'm going to rewrite this so that I have x squared plus 6x plus 9 minus 9, and then keep my plus 13 at the end. And so I'm adding and subtracting 9 because that would be the equivalent of adding 0. So I haven't actually changed the value of my expression. I'm going to take the negative version of the number I wrote out. And so this is going to give me x squared plus 6x plus 9 minus 9 plus 13. And then I can factor the stuff in the brackets to get x plus 3 squared and then plus 4. So what that means is I can rewrite this as 1 over x plus 3 squared plus 4 dx. And I can see that this sort of looks like this inverse tan integral where I have the a squared. So instead of an a squared, I have a 4. So this means that a is 2. And instead of an x squared, I have an x plus 3 squared. So this means that my x is x plus 3. Now, this is terrible notation because this x and this x are not the same x. This x is from my tangent expression up here, and this x is from my x plus 3 squared. So this is not great notation, but we'll roll with it. So what that means is that my integral is going to be 1 over a, or 1 over 2, times inverse tan of x over a, but my x here is actually an x plus 3, plus a constant. Now, there's a new notation that you see in your textbook, and that is something called arctan or arcsine or arc cosine, and that is simply a different way of writing inverse sine. So this is the same as saying arcsine of x. This is the same as saying arctan x. It's just a different notation, and it's used in some textbooks. It could be used on the AP. And because the little negative one there, sometimes people get confused. Are we doing an inverse? Are we doing a reciprocal? Which notation is that? So sometimes arctan or arcsine are used. Okay? So we can also write this as 1/2 arctan of x plus 3 over 2 plus c. And it's just two different notations. There's no mathematical difference in my answer. So there's two things here. One is completing the square, and one is noticing the pattern that we have two things squared adding together, and that kind of looks like our integral of 1 over a squared plus x squared. Our next skill that we're going to learn is, well, what if we've got a rational? We can't split it up in our usual way. And so how can I simplify this? And our skill that we need to call is long division or synthetic. So I prefer long division. Some of you might prefer synthetic. Either one is fine. It's not the technique here that matters. What matters is that you're able to rewrite this thing. So if I do long division here, I'm going to get x squared plus 3x. And if I add 1, multiply the 1 out, I get x plus 3. Subtract that, I'm going to get 2. So I get x plus 1 with a remainder of 2. And I should get the same answer when I do synthetic. So I bring down the 1, multiply the negative 3 and the 1, I get negative 3. Add those together. That gives me 1. Multiply the negative 3 and the 1. Add those together. That gives me 2. So this is going to give me x plus 1 with a remainder of 2. So what that means, if we recall from Math 12, this means that we have a division statement. It says x plus 3 times x plus 1 with a remainder of 2 is equal to x squared plus 4x plus 5. But I didn't start my integral with an x squared plus 4x plus 5. I had x squared plus 4x plus 5 over x plus 3. So if I divide everything here by x plus 3, I end up with x plus 1 plus 2 over x plus 3 equals x squared plus 4x plus 5 all over x plus 3. So what that means is I can rewrite my integral. Because my original integral was this, I can rewrite my integral using my new expression. So my original integral was x squared plus 4x plus 5 over x plus 3. And I can rewrite it as the integral of x plus 1 plus 2 over x plus 3. Now we can split this up into two integrals if we want, or we can just find the antiderivatives from here. So my integral of x is 1/2 x squared. My integral of 1 is x. And my integral of 2 over x plus 3 would be 2 ln x plus 3 plus c. And if we want, we can bring this 2 in front of the ln up as an exponent and write it as 1/2 x squared plus x plus ln x plus 3 squared. See, either of those would be fine. These types of questions are usually in multiple choice. So if you don't see your answer, it might just be that you need to simplify differently. And again, if you don't like going straight there, you could break this up into the integral of x plus 1 dx plus the integral of 2 over x plus 3 dx, but you would get to the same answer. And our last example here, again, is we need to break some stuff up before we can start. We can tell this sort of looks like there might be something with inverse trig because we've got that x squared plus 1 on the bottom, and we know that the integral of 1 over x squared plus 1 is inverse tangent. So the problem is on the top we have this x plus, but I know that I can break this up into two fractions, and I can rewrite this as the integral from 0 to 1 of x over x squared plus 1 messy, let's fix this, plus the integral from 0 to 1 of 1 over x squared plus 1. And so there we are on the right-hand side, we already have an integral that's easy to evaluate. The left-hand side, we need to do a bit more work. We are going to need to use substitution. I could write the word substitution. So I'm going to let x squared plus 1 equal du, or 2x dx, equal u. 2x dx would be du, or x dx is 1/2 du. And I also know if x is 0, u would be 1, and if x is 1, u would be 2. So what that means is I now have a new integral 1 to 2 of 1/2 1 over u du plus the integral from 0 to 1 of 1 over x squared plus 1 dx. Now, it doesn't matter that we have two variables here because we're going to be plugging numbers in and evaluating, so their variables are all going to go away. If we did not have bounds on our integral, then we would be substituting back in the u in the first integral, and we would end up with all x's anyways in our antiderivative. So it's all right here that we have two variables because they're all going to. So this one is going to give me 1/2 ln u from 1 to 2, and the other one's going to give me inverse tangent from 0 to 1. And when I evaluate this, this is going to give me 1/2 ln 2 minus 1/2 1 plus inverse tan of 1 minus inverse tan of 0. Now, again, another reminder that if we have something like tan theta equals x, then inverse tan x is equal to theta. So if I wanted to find inverse tan of 1, I'm looking for an angle where tan of that angle would give me 1. And for inverse tan of 0, I'm looking for an angle where tan of that angle gives me 0. So here, what I want to know for this one, for example, is tan of what is equal to 0? That's what I want to know, right? And tan of 0 is equal to 0. So that means that inverse tan of 0 is equal to 0. And for this one here, I want to know tan of what gives me 1. And I know that in that case, theta would be pi over 4. So what this means is that inverse tan of 1 is equal to pi over 4. We also know that 1/2 ln 1 is equal to 0. So what this means is we have 1/2 ln 2 minus 0 plus pi over 4, because inverse tan of 1 is pi over 4, minus 0, because inverse tan of 0 is 0. And so that's it. That's all we have. And we could fix this up and write this as ln 2 to the power of 1/2 plus pi over 4 if we want. Or we could write this as ln root 2 plus pi over 4 Again, any of these would be okay. This would likely be in a multiple choice section. And so if you don't see your answer, require some simplifying. You could also write, instead of inverse tan, you could be writing arc tan in all these places. Okay? So the last trig integral that I promised you is down here, that results in an inverse trig function. So those are the three that you would see. You would see integral that results in inverse secant, inverse tangent, or inverse sine. And there's this one that might be helpful as you go through some of these questions and integrals that are a little bit trickier. So you might be able to find some integrals in chapter 5 as well that we might have skipped over that have some of these. But a helpful fact is if you integrate from a to b of f of x dx, this is equivalent as integrating from a to b of f of a plus b minus x dx. Okay, so make sure you know those inverse trig integrals and this little helpful fact, and you should be able to get through those board questions. Again, some of them are tricky.